Hello everyone and welcome. In this video I'm going to be implementing a complete binary search tree in C++ and all of the main operations it can perform. Now if you don't know what a binary search tree is or how it works, I'd really recommend you watch my previous video where I actually explain everything, because I'm not going to do that in this video. In this video I'm solely going to be explaining the implementation front end code and not the concepts themselves. Okay. So let's get right into it. The first thing I'm going to do here is create a struct, which is going to be representing the elements of my tree. I'm going to call this node, and in here I'm going to put a couple of things. First, we're going to have the value itself of the element. I'm going to make this an integer for simplicity's sake. And then we're going to have two pointers of the type node. So essentially the node inside is going to have two pointers to another element of the struct node of the type node, and these are going to represent the children of this node. So we have a left child and a right child. Now let's actually insert some elements here onto our tree. So first of all, let me create here an insert function. This is going to return to us a node, and it's going to take in the value here, and it's also going to take in the root here of my tree. So the root is essentially the top element of the tree, right? Now I am going to be allocating memory for new nodes, and I am going to be creating new nodes inside of this function. So I'm actually going to create here a function in order to do that. This is going to return a node as well. Let's call this create new node, and it's going to take in the value of the new node. So I'm going to create here a new node variable, and like I said, I'm going to allocate this on the heap. So I'm going to use new node like so, and now let's just initialize here the values. So let's say that the value is equal to the value that I pass into my function. My left child in the beginning is going to be null because it doesn't really have any children, and the same for the right. So this is going to equal null, and then all I have to do is return the new node like so. So this is going to be our create new node function. It's going to take in a value, allocate memory for a new node, initialize its values, and then return it. And now in my insert function, I'm going to have a couple of cases. I'm going to say if the root is equal to null, then that means that our element doesn't have, our tree doesn't have any elements, or we've reached the end of a branch and we just need to add the node right there. So here I'm going to return create new node with the value like so. So essentially this is going to put this node in that position. Okay. Now, if the value that I pass in here is smaller than the root dot value like so, then that means that we need to insert this node to the left of the root, right? To the left subtree of the root. So in this case, I'm going to say that the root left, so the left child of the root, is going to equal, and I'm going to recall insert with the same value, but this time I'm going to pass in the root left, right? Because I need to put the element at the left of the root. Right? And otherwise, that means I need to put the element at the right of the root because it is greater than the root itself. So I'm going to say that the root dot right is equal to insert. And in here, I'm going to pass in the same value. And now I'm going to say root right like so. So let's go over this one more time. So if our root is null, it means that we don't have any elements or we've reached the end of a branch. It means we're going to put the element in that position. So I just need to return a create new node, which is going to return to us the new node that we just created, right? Now, if the value of my new node is smaller than the value of the root, then that means I need to put it at the left of the root. So I'm essentially going to recall insert in a recursive manner with the same value, but this time I'm going to insert it at the left of the root. So I'm going to put it at the left subtree. And otherwise, it means that the value is greater than the root. So I'm going to say that the right child of the root is going to equal insert the same value, but at the right side of the root. All right, that's all this does. And I'm actually going to turn this into an else if. Now, in the end, I'm just going to return here the root. Okay, so this is going to be our insert function. Now, how do we actually do this? Well, first of all, we need here a node. This is going to be called root, and this is going to represent the beginning of our tree, right? So this is going to be the root of our tree. And essentially the way we use the insert function is we're going to say that the new root is going to equal whatever is returned to us by the insert function. So for example, let's insert 10, let's pass in here the root. And this is going to create basically a tree with the element 10. And we can do this a couple of times, give it a few values. All right, so now that we've inserted a couple of elements onto our tree, let's create here a way for us to see the elements of our tree. So I'm going to create a void here called traverse. And with this, we're going to essentially traverse our tree. So essentially go through every node of the tree in a certain order. And in here, I'm going to do in order traversal, meaning we're going to get the elements sorted by increasing order. So how do we do this? Well, first of all, if the root is equal to null, then we're just going to terminate our function. So I'm going to return. Now, otherwise, in order is essentially we're going to go to the left child, then we're going to go to the root itself, and then we're going to go to the right child. So we're going to first traverse here the root left, like so. Then when we're done, we're going to see out the root value and a \n like so that we can actually see, and then we're going to go to the right side or to the right subtree of the root. So traverse right. Okay, now let's actually see if this works. I'm going to say here traverse our root like so, and let me pull this up. Let's see if this works. I forgot to initialize here my root at null like so. All right, so let's try this again, see if it works. All right, perfect. And as you can see, we have gotten the elements in a sorted manner. So everything is working correctly. Now let's make here a search function. This is essentially going to be the same as insert, but instead of insert here, I'm going to call this search. And the way we're going to do this is if the root is equal to null, then that means that we've reached the end of the tree and we haven't really found our element. So we're just going to return here null. Now, if the root value is equal to the value that we pass in the value we're searching, then we're going to return the root, right? Because if the values are equal, that means we have found the element we want. Now, else if the root value is essentially greater than the value, we're going to have to search in the right side of the tree, right? So we're going to return search root right, like so. Or sorry, we're going to search in the left side of the tree. I apologize. So this is not right. This is going to be left, right? Because if the value is smaller, then it needs to be to the left of the root and not to the right. Okay, I apologize. And otherwise, that means that the value is going to be greater than the root. So then we're going to have to search at the right. Okay, so we're going to return here. This is a return statement like so. Search to the right side, and this is essentially going to be our search function. Let's see if this works. I'm going to see out here search, and let's search, for example, for 2. I'm going to pass in the root as well, and let's see out the value here to see if we have actually found 2 or not. And there you go. Now this outputted everything smushed together because I didn't add an end line, but essentially 2 is here and we have found it, and that is what matters. So let me comment this out, and that is the search function. Now the last function we need is going to be the remove function. However, before that, I want to create 2 very simple functions to find the maximum and the minimum values of the tree. So both of these are going to return nodes. The first one is going to be called max, and it's only going to take in here the root. So essentially, to find the maximum element in the tree, all we need to do is go right? Because if we go right enough times until we reach essentially the end of the branch, we're going to find the greatest node. That's literally the definition of binary search trees, and that's the property that make them a binary search tree, right? So I'm going to say, if the root dot right is different from null, then we're going to return the max, but instead of passing in the root, we're going to pass in the root right, like so, right? So if the root dot right is not null, then we're going to go to the right. We're going to keep going to the right. Now, otherwise, we're going to essentially return the root, right? Because if the root at the right, if essentially the right child of the root is null, then that means that that is the last child to the right, if that makes sense. So we're just going to return it because it's going to be the maximum value. I don't know if that made sense. I hope it did. And the same thing for minimum. I'm going to grab this. I'm going to change this to min. And now everywhere that says right, I'm going to change to left, right? Because if we go left all the time, that means we're going to find eventually the minimum element. So those are really easy functions. And now let's actually implement the remove, which is a little bit more complicated. This is going to return to us the element that we're removing, and it's going to take in the value of the element we want to remove, and of course the root, like so. Now for the remove function, we're going to have to search first for the element we're looking for. I'm going to say here, if the root is equal to null, essentially we haven't really found the element we wanted, it doesn't exist, so we're just going to return null. Now else if the value of the element we want is smaller than the value of the root, then we're just going to say that the root left, right, because the value is smaller, is going to be equal to the remove function again with the value, but this time we're going to pass in the root left, like so. So essentially, if the value is smaller, we look to the left, and if the value is greater, we look to the right. So root right is equal to remove, and in here I'm going to pass in the value and the root right, like so. So now that we have found our element, I'm going to say else. So essentially, if the value is equal to the value left, right, we're going to do a couple of things. First, I'm going to create here an auxiliary variable. And what is this telling me here? Okay, so I added two else statements. So let's make this an else if statement. So let's say value is greater than root value, and this should work now. All right, so first we have an auxiliary variable. Now I'm going to say if the root at the left is not equal to null, so essentially if we have a left child, and if the root to the right is not equal to null, so essentially, if the node that we want to remove has both a right and a left child, it has two children, then we're going to have one case. Now, otherwise, that means that either the node has one child or it doesn't really have any children. So this case is easy. I'm going to say that the auxiliary variable is going to be the root. I'm going to say if the root left is equal to null. So essentially, if it has a if it doesn't have a left child and the root right is equal to null. So if it doesn't have, if the element we want to remove doesn't have any children, all we need to do is say that the root is equal to null. So essentially, we just say that our element is equal to null. Essentially, we just remove it. Now, else if the root left is equal to null, so essentially, if we have a right child, then I'm going to say that the root is equal to root right? Because if the element only has one child, essentially we exchange the child with that element. And otherwise, I'm going to say that the root, I don't need these curly braces. I'm going to say that the root is going to be equal to root dot left, like so. So we've essentially removed the right child, okay? And now in the end, all I need to do is say, with a tab here, delete our aux, right? So let's go over this one more time. I said that my auxiliary variable is going to be the root. Now, if the root left is equal to null and the root right is equal to null, our root doesn't have any children. All we need to do is set it to null and we've removed it. Now, otherwise, if it has a right child, then our root is going to equal that child. And if it has a left child, then our root is going to equal that child. And then all we need to do is delete the root. So essentially remove it from the memory. Now let's do the other case where our variable, or sorry, our element has two children. This is a little bit more confusing, but we can do it. So the first thing we're going to do is say that the aux is going to be equal to the maximum. And if you remember, in this case, we need to find the maximum element to the left of the element we want to remove. So I'm going to pass in here the root left. So now our aux is going to be the maximum element to the left. Then I'm going to say that the root value is going to be the value of aux, right? So I'm essentially going to exchange the value of the element we want to remove, which is the root, with the value of the maximum of the root to the left, if that makes sense. And then I'm going to say that the aux value is going to be the value of the element we want to remove, right? So essentially, we're exchanging the values of the root and the auxiliary variable, which is the maximum of, well, the left subtree of the root. Sorry if this is confusing. And then I'm going to say that the root left is going to remove, essentially, I'm going to pass in the same value, but in this case, I'm going to pass in here the root left. So again, let's go over this one more time. So if the element we want to remove, which is our root, has both a right and a left child, we're going to have to exchange the element of the root with the largest element to the left of the root. So essentially we say that the auxiliary variable is going to be the maximum element to the left of the root, and then we're going to exchange the values of those elements, right? So the value of the root is going to be the value of the greatest element to its left, and the value of the greatest element to its left is going to be the value of the root. Then all we need to do is say that the root left, so essentially the left subtree of the root, is going to equal remove that same value but from the left of the root. And this is going to fall in one of these cases where essentially our the element that we want to remove has 1 child or 0 children. Okay, so I hope that makes sense. Now in the end, down here, all I'm going to do is return the root. Oof. Okay, so that is it for the remove function. Let's actually see if this works. So I'm going to say here that the root is going to equal remove, and let's remove, for example, 22. Let's pass in our root as well, and then we're going to traverse the tree. So I'm going to run this code and let's see if 22 is there. It is actually not, so that means that we have successfully removed it from the tree. Let's try another element, for example, 15. Now 15 is not in there. 10. Now 10 is not in there. 6, for example, and you get the idea. Oops, let me run this again. All right, you get the idea. So that is the remove function. And that is actually all I wanted to show you today. This is how you implement a binary search tree in code. I hope this video was helpful. If it was, please like and subscribe to support the channel. Thank you so much, and I'll see you in the next video.